pulled something from, I squared R. This was what? This was chapter 25, I think, when we wrote this. Right? Except that just about the problems, all the problems that we did back then, the power was always, it was a DC circuit. The voltage of the battery was always the same. So the current was always the same. So the power dissipated was always the same, as long as the circuit existed, right? So we didn't run into this issue where, what happens if the power is changing with time? How do I get the energy out of that? You integrate the power with time. So that's something new. You come across this integral e to the minus something t dt. It's not supposed to be a difficult one. Maybe you don't remember it, but it's an integral that shows up a lot, and as you'll see it again in other courses and again, then you say, oh, that's an integral that I should know, and then you'll be able to work with it more comfortably. Let me do this other example. Question?
Will we have to account for friction ever?
No. I mean, we could, but it just makes the problem. But what happens is that the way that it was, that was a differential equation. It was just of the first order with only one term, so it was very easy to separate the variables. If you add a drag force, like air friction, which depends on the speed of the thing going through. So if you add a frictional force that also depends on the speed, then it becomes a more complicated differential equation, and then it's beyond the scope of this class. So you in this class, no. Later on, most likely. Look at this one. Look at the second one. I'll blow it up so it's easy to see. A square loop, that's this guy here. Square. Actually, I don't like that S. Can I call it L?
Yeah.
S it looks too much like a 5. But anyway. Or yeah, I'll just call it. And I don't like this A over here. This distance A, because this thing is going to be accelerating. So then you may confuse that distance with acceleration A. So I'll just change some numbers, okay? Some letters, some names. So a square loop of side L, let's say, lies on a table near a very long straight wire, which I don't like the word carries, which has a current I, as in the figure below. So there's a square loop on a table, but it's square, right? And there's a very long straight wire with current I in it. All right? Calculate the magnetic flux through the loop. What is the magnetic flux through that loop? All right? So let me erase this. This will be extra example number 2. By the way, the problem that I just did, if you imagine that's a homework problem, it'll take maybe a couple of pages to come up with the solution, right? So, those days where you do a problem on, half a sheet of paper, they're coming to an end. You get out of OCC and that's the end of that. Wherever you're going to be transferring to, you're going to be doing homework problems which may require 5, 6, 7, 8 pages. So, just so that, just to give you sort of like an intro to that, right? So we have a very long wire like this, straight. The current, I put it to the right. And there's a loop, a square loop over here. I'm gonna put it like this. How about I call this distance, later on we're gonna pull it up, I think. So if someone now pulls the loop directly away from the wire, how about we call that distance y? Is it okay if I call this distance y over here? All right, because later on we're gonna pull it up and then that y is gonna be changing, right? And when we calculate the magnetic flux and we differentiate it with respect to y, but with respect to time, it will throw in a dy dt, which is the acceleration, which is why I don't want this to be called a. So anyway, that's because of what's coming up later. But for this part, the loop is just steady there at a distance y, and let's call the side of this L and L, if that's okay. Now, it looks like a rectangle, but
it's a square.
it's supposed to be a square, right? So it's L and L. Square loop, right? So the first question is, what is the magnetic flux through the loop? Right, so I want to know this. So it's the magnetic field multiplied by the area of the loop. Now you tell me, is the magnetic field everywhere throughout this area the same? Generated by the current in this very long wire. What is the magnetic field generated right there by this wire, by the current in this wire? Do you remember? Chapter 28. Magnetic field of a very long straight wire, current I in it, at a distance R. Mu naught I over 2 pi R. So it depends on this distance. So the magnetic field here is different in magnitude from the magnetic field there, from the magnetic field there, from the magnetic field there, because all of those distances from the wire are different. So the magnetic field is not uniform throughout this loop. So how do we calculate the magnetic flux? We can't just say A times the area. I mean, don't do this. Don't say, oh, it's mu naught I over 2 pi R times the area, which is L squared. Very bad. That's very bad, right? It shows that you didn't realize that the magnetic field, at the different locations in this square loop, right, at different distances away from the wire, the magnetic field is different. So what do? So we say, okay, I will say that over this length over here, at this distance R, the magnetic field in there, right, is mu naught I over 2 pi R. And I will take an infinitesimal length, so small that I can think of the magnetic field in here as being constant. So I'm going to call this dr, this width over here, dr. So that the magnetic flux through that strip, what is the magnetic flux through this strip over here? Let me call that d phi. So that the magnetic flux through the strip is the magnetic field over that strip, which I assume it to be constant, times the area of that strip, which I'm going to call it the A. Now you tell me, what will be the area of that strip if its length is L and its width is dr? What will be the area of this strip? Maybe I should use a different color for the area of that strip. So it's this. So what is the area of that? LDR, exactly. It will be the length, right, times the width. So the magnetic flux through that strip is mu naught I over 2 pi R times LDR. Right? That's the magnetic flux through that strip. That's this guy. What I want is the entire magnetic flux through the strip. So what do you think I should do? Which is the variable here?
R.
R. So I have to integrate both sides, right? So I'm going to pull out the constants. Mu naught I, L, 2 pi, and there we go. And I integrate from what value of R to what value of R to get the total magnetic flux through the square loop.
From Y to
From R equals
Y.
Y all the way up to R equals
Y plus L.
Y plus L. Right? This is Y. And all of this is Y plus L. So you integrate from R equals Y to Y plus L. And that's the total flux. That is the question that we're asked in this part of the problem. So let me raise that, do that integral on that side of the board. So let me get rid of this. By the way, these two examples are from other textbooks, not from this textbook. Obviously, I thought that there was something to them to then decide to do them in class. So, so this is going to be what? The magnetic flux equals what? Mu naught I L over 2 pi, and that's going to be the natural log of R integrated from Y to Y plus L, right? So this becomes magnetic flux equals mu naught I L over 2 pi times the natural log of, can I take a shortcut? Y plus L over Y. Or if you don't, actually it's okay. I mean, we can just leave it like that, or mu naught I L over 2 pi, and then you can say the natural log of Y plus L minus the natural log of Y. So either one of these is a good answer. So the next question asks, if someone now pulls the loop directly away from the wire at speed v, so now somebody's going to pull this up at speed v, what EMF is generated? In what direction is the induced current in the square loop? So what will be the EMF generated? Notice we were not giving a resistance, so they're just asking for the EMF. But if they wanted the induced current, it would be the EMF induced divided by the resistance of this square loop. But they didn't give us that, so we'll just calculate the EMF. And what would be the direction of the induced current? Can you tell me, using Lenz's law, what would have to be the direction of the induced current in the loop? As the loop is pulled and, move this way at speed v. What's happening? Which way is the magnetic field through that loop? Is it into the board or out of the board?
Out of the board.
Right, so current in the wire is like this, and the magnetic field is out of the board. So it's out, 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 out. As this loop is moved away and away and away from the wire, the magnitude of this magnetic field is going to get smaller, 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 smaller. So the loop is going to say, I'm losing flux. I'm going to try to make its own magnetic field this way. So the current is going to be, the induced current is going to be clockwise. Oh, sorry. I'm moving it up, right? So it's out, I'm sorry, I should have written out. I'm moving it out, so it's getting smaller, smaller, smaller. So it's, no, I'm losing that, so it has to be counterclockwise, the induced current. Better, right? Sorry. And looking at that, then it's... So the EMF will be the derivative of this flux with respect to time. And the minus sign is just there to tell me something about the direction of the induced current, but I figured that out using Lenz's law. So, okay, I'll just leave it there for the moment. In the end, I'll just get rid of it. So what is the derivative of this with respect to time? A minus mu naught I L, these are constants. What is the derivative of this natural log of y plus L? Y is a variable, y is changing, right? So how do you take the derivative of the natural log?
1 over.
It's 1 over that thing, right? Which is 1 over y plus L, times, by the chain rule, times the derivative of the argument inside. L is a constant, so it'll be dy dt. Minus, for the other one, is going to be 1 over y times the derivative of the argument dy dt with respect to time, dy dt. But dy dt is the speed, right, at which you're pulling this thing up. Right, this v, this is the rate at which this distance y is changing. L is a constant. So therefore this becomes equals minus mu naught I L over 2 pi times v over y plus L minus v over y, right? Okay, let me see if I can simplify that. It's mu naught I L 2 pi, the v is everywhere. I can multiply this two in the denominator, and that becomes a y minus y plus L. So this will cancel that, and the minus L will cancel that. I mean, the minus sign will cancel that, so this will be mu naught I L squared of times v over 2 pi y plus L. And the induced current will be in the counter clockwise. Right, so as this bar is pulled up, away and away and away, the induced current will be in this direction. To generate the magnetic field, making up for the loss in magnetic field as this loop is being pulled further and further away. Let me see, did I make a mistake? No one has said anything, so probably I didn't. No, it's good. Last question. What if the loop is pulled to the right at speed v? Suppose I grab this loop and I pull it to the right at speed v. What will be the induced EMF?
It'll stay the same.
What will be the induced EMF? If I grab this loop, there's the wire, horizontal, very long, and instead of moving the loop upward, farther away, I move it to the right.
What the flux through?
Quick. Is the flux changing?
No.
So there's no induced voltage. You know, right? If I move it away, I have smaller magnetic field here. If I move it closer to the wire, I have bigger magnetic fields over here. But if I move it this way, it is different throughout, but it's the same magnetic flux, so there's no induced voltage. So in part C, the EMF induced is 0. Therefore, the induced current is also 0. The magnetic flux is not changing. Remember, it's only when the magnetic flux is changing that there will be an induced voltage, which will lead to an induced current. When do we see each other again?
Monday.
Monday, I am going to go over the last example. On the transformer. And this example only takes literally, when you think about it, it only takes 1 minute to do. But, so in the transformer there are 2 coils. So what we're going to do next week in the lab, and it's gonna be the last lab that we do next week,
Yay.
is I'm gonna give you a transformer to build. So I'll give you a set of coils, and with different numbers of turns, and then you're gonna build a transformer that will double the voltage that you put in, quadruple the voltage, multiply by a factor of 8, and also maybe half the voltage, reduce it by a factor of a half. Okay, so you play with it. So that'll be the last lab that we're gonna do. But instead of putting the two windings on the same unit over here, this just makes the solution to the problem easier. We're gonna have the two coils separated, and you'll see how we're gonna. So I'll talk about that next time on Monday. On Monday, the next time. All right. For those of you who did the lab on Monday, remember that when you write the lab report, right? The idea is to do a graph where you plot the magnetic field as a function of distance, right? And you're gonna fit your data points, and when you do that, when you fit the curve to the data points, the computer that you use to create that curve will give you y, something in terms of y and x, like maybe 22, I don't know, 350 x to the minus 3.7, for example, right? When you write the report, please do not write this. I don't want to see when you write the report a y equals something, x something. Right? This is not math, this is physics. So the y represents this. So in the report you write b, that's the y, b is the y, and then you write that. And then don't say x, it's a distance. Well, I guess you put, do something like this. I want to see a b and I want to see a distance, right? Don't write a y on x, right? That's from math. We're applying it to this specific problem. So use the variables
But isn't x usually
that they
displacement?
represent. So what's that?
Isn't x usually displacement?
Yeah, but x is a distance. You could call it a distance.
Okay.
But in the lab handout, we called it d. So
Okay.
let's just be consistent with that. And the rest of you, I'll talk about that lab in about an hour, I guess. All right, I'll see you.